Hi, my name is Kevin Heng. I'm an exoplanet scientist who is focused primarily on the atmospheres of exoplanets. So the reason why they're interesting is because beyond mass and radius and bulk density of an exoplanet, you can't really say that much about an exoplanet unless you know something about its atmospheric chemistry. And so there's a whole blossoming field in exoplanet science that's very young, that's trying to measure and understand and interpret the atmospheric chemistry of exoplanets, and this is this is the area that my research group and I focus on. So one of the techniques we focus on is using Bayesian inference to analyze spectra of exoplanets. So you want to go from a spectrum to saying how much oxygen or water or carbon dioxide or methane you have, but this procedure is fraught with uncertainties. So for example, you could have model degeneracies where many different combinations of parameters would give you basically the same spectrum. So you need to deal with that. That's not the topic of this talk. A second obstacle is to basically our incomplete understanding of certain types of physics. And one of the big themes that has come out in many different fields, so planetary science, Earth climate science, exoplanetary atmospheres, brown dwarfs, is actually how the presence of clouds or hazes or aerosols in general confuses the interpretation of these spectra. And so in this talk, I'm not going to give you the answer to how to solve the long-standing mystery of clouds and hazes and aerosols, but I think we have developed a tool to move this forward in the right direction. And the reason we are interested in this is because at the end of the day, astrobiologists would like to do things like measure the amount of water and carbon dioxide and oxygen in the atmosphere, but your ability to do that accurately is actually confused greatly by the presence of clouds and aerosols and hazes. So if you could figure out a way to constrain from the data the properties of these clouds and aerosols and hazes, then you can get more accurate chemical abundances. So in this talk, I report on what I consider to be an exciting discovery. So we found basically solutions that you can write down on pen and paper that describe how a planet or a moon reflect light across wavelength. And one of the reasons we are so excited is because this problem was posed in 1916, so 105 years ago. So it's the general but approximate solution to a 105-year-old problem. But most of my astronomer friends are not excited by mathematics, even though I find it intrinsically interesting. What is more exciting are the implications for data analysis, as I described to you. So I'll give you two examples. I'll use the new solutions of reflected light to analyze Kepler data of a hot Jupiter, an exoplanet. I will also use the same solutions to analyze Cassini data of our Jupiter. And in both cases, I will show you that these solutions combined with a Bayesian inference framework is a very powerful way of getting fundamental physical properties of these aerosols. And hopefully in the future, this will move us in the right direction of constructing robust Bayesian inference frameworks for planets that will hopefully host some sort of biogeochemistry. And with that, I look forward to seeing you at my talk.